Thanks. Yeah, everyone. Welcome to my talk on observability for Dask in production. As I was already introduced, I'm Hendrik Makait. I work as an open source software engineer at Coiled. Coiled is a company itself, not only maintains Dask, but we also provide managed Dask service. So we take care of basically deploying it for you into your cloud account, so you don't have to worry about all the nitty-gritties of connecting VMs, setting up networking, etc. I'm on the open source side, so I work in particular on the distributed engine of Dask and make sure that this is maintained but also enhanced. So before we dive into observability, let's take a minute to talk about Dask, what Dask is, how it works, and why it's useful. Now, fundamentally, Dask is a library for general purpose parallelism in Python. What that means is that it can take basically any workload you have and parallelize it. It's like multiprocessing, but on steroids. The easiest example would be something like this, where we have a bunch of files that we just want to process in an embarrassingly parallel fashion. No interactions between the tasks. Dask can do that for you. But Dask can do much more than that. So if you have data frame workloads that are written in pandas code, or if you have something that array computations that are written in NumPy or X-ray, Dask has implemented parallel versions of those libraries that not only mimic the APIs that those packages have, but they also use them under the hood, so the semantics are exactly the same. What that means is you don't have to rewrite all your code to make it work in a different parallel framework, but also, even if the API would be mimicked in some other libraries, they might function slightly differently, which might sneak bugs into your code. With Dask, it works exactly the same. But since Dask is a general purpose library for general purpose parallelism in Python, you can take any workload, however dynamic or complex it may be. So you could take very custom algorithms, machine learning things, and could end up with some algorithm, some computation graph that looks like this very complex example up there, and Dask would be able to help you parallelize that. Now, Dask is not only a library for parallel computations in Python, it also comes with a distributed runtime engine. And what that means is that Dask can not only take your computations and parallelize it across, say, all 8 cores that you have on your laptop, but instead it can take your workload and parallelize and distribute it onto a cluster of hundreds or even thousands of machines. And that, in essence, means for you that your very complex computations, your very long-running tasks might actually run much faster because you have way more CPUs to process them on, and you also can process much larger data sizes. There are various deployment options for this. Basically, what you have available, there should be a way to deploy Dask on that, whether that's an on-prem Kubernetes cluster. There's an open source solution for that. You can also deploy Dask on an HPC cluster. And there are various ways of deploying Dask in the cloud. For that, you can either use some open source solutions, or you can use a managed service like Coiled, which takes the deployment pains away from you. You just tell us how big your cluster should be, and we do the rest for you. So let's make this a little practical so that we all know what I'm actually talking about. And for this, I have 2 questions to the audience. First, who here likes very, very polished demos that just function well? A few people like that. That's good. Now, who's more on the destructive side of things? Who likes things that blow up, break? Nice. The good news is I have an example for both of you. So I have a very polished demo that totally blows up Dask, because an observability talk where everything works as it should be is kind of boring, I guess. So let's get started. In this example, I've just spun up a cluster on Coiled with 20 workers, and we have a relatively simple workload. I'll just start this. And what we do is we read in a bunch of files, quite a large data set. We group that by some columns, and then we just calculate some aggregate statistics like medians and standard deviations. And then in the end, I want to have the result back as an output. That should fit onto my local machine, so everything should be fine. And here we can now see, okay, our computation has started. And if I go actually to the Dask cluster dashboard, we see, yeah, things are processing. We see here that how much bytes we have stored in memory, that cluster is not overloaded in terms of memory usage. CPUs are quite utilized. Things are chugging along nicely. We can also dive deeper into the individual workers, see some statistics about them. And then there's like a lot more data we can see about the cluster on here. Now, if I go to call it, there's even some more information that I have about this cluster. First of all, we actually have the computation that we're running, so you can correlate that with things that might happen. Then we have some more metrics on this cluster that we collect and can show. And in the end, of course, logs. Logs are great. Logs tell us many, many things that happen. Let's see. There's a lot of information in here. And now let's check what's happening. Oh no, things broke. For some reason, this has stopped working. It's throwing an error, and it's a pretty long error message. And in the end, it tells me like, well, yeah, your P2P shuffle broke. That's useful. I know what happened, but why? I have no idea why this is. So what I would like now is some sort of system, some sort of mechanism that tells me like, what has been going wrong? Why have we failed here? Well, in other words, what I want to have is observability. So what is observability? Let's get everybody on the same page here. I quite like this definition from the OpenTelemetry project, which says that observability lets us understand the system from the outside without really knowing what's going on the inside. It allows us to ask questions about this system. It allows us to troubleshoot it. And quite importantly, it allows us to ask novel questions and handle novel problems in that. So that are the problems that we have not created an alert for in the very beginning, but that have just popped up and we just realized something went wrong. And it also allows us to ask the question of, why is this actually happening? So in essence, yeah, observability is just a property of our system that allows us to take various activities like monitoring health, root causing bugs, or just analyzing performance and optimizing hardware utilization. How do we make a system observable then? For that, usually we talk about 3 pillars of observability. Those are logs, those are metrics, and tracing. In this talk, I'm actually going to skip tracing because that's a very complex topic and it should be a talk of its own. Like, I don't have the time to dive into everything here, unfortunately. What I wanted to talk about instead is also diagnostic tooling. So it's nice if we have the telemetry data collected somewhere, but we actually want to be able to interact with it. We want to be able to ask questions about our system and understand what is happening and why it is happening. And that's what the tooling is for. So let's first talk about logs. I think we all know them. It's this stream of text that's floating by on our screen when we're tailing the output of some program that's running on a computer. There's like lots of stuff in there, lots of good stuff in there, but also can just be overwhelming because of the pure mass of it. Now, before we dive into the juicy bits of logging in a distributed system like Dask, let's actually talk very briefly about like best practices we should already be following. First of all, don't use print for logging. Like, print is bad. If you don't know why print is bad, I recommend you to go to the documentation of your favorite logging library and just read through it. You'll learn a lot of things there, and you also see that you're missing out on a lot of features if you rely on print to get some output, or if you get some message into your standard out. The next important thing is provide me with the necessary context. So in Dask, for example, if you try to, or if you're just removing a worker, don't just tell me, yeah, I'm removing a worker now. That doesn't help me. Like, tell me which worker that is. Tell me why you think that is a good idea or why you want to do that in the first place. Just give me all the context I need to understand the situation. And finally, a little bit of an advanced usage of logging, but what I still recommend is use structured logs. If you have logs that are structured, that enables a whole new use case where you can actually use machines to read in, parse in those logs without having to write overly complex registers over various strings. And that will allow you to also analyze your data and identify critical situations. Now, if you're following all this stuff, you may think like, sure, I'm doing that. Am I done now? Is that all there is to logging? And if you're working on a single node machine, if you just run your program on your laptop, you might actually be done now. But keep in mind, we're talking about Dask and a distributed system here. And that changes the game quite a bit. Sorry. So let's consider this situation. I have a workload and I suddenly spin up a cluster of 100 workers. I don't have it just running on my local laptop. What's happening now? Well, congratulations. You have now 102 places to look for logs. And I don't know how you feel about assets aging into various cloud VMs, figuring out where the log files live and like piping them through some grep commands. I'm not a huge fan of that. There should be a better way to do this. And one of those ways is actually built into Dask already. So you can use the client to get scheduler logs. You can use the client to get worker logs. You can even like just get the logs of a specific worker if you know something has happened on that machine. That's great, but it's also a bit problematic because this only works as long as your worker is alive and it responds to your queries. Now the issue is when we look into logging, it's usually because something bad has happened already. So chances are that worker is long dead because either it's just been killed by something going horribly wrong, or we've just detected this situation like a day after something actually happened and now we're trying to figure out what's going on, but the worker is long dead, we have long shut it off, and it's not alive anymore. And if it's not alive, it doesn't answer your request and it sure as hell doesn't return any logs to you. So what you want to do instead is that you want to centralize your logging. What that means is, in essence, you take all the logs from all the machines you have and ship them over into some external system. And that external system will take care of, first of all, storing all that information for you, making sure that it's durably available after the fact. So when we dive into debugging mode on a Monday morning for a workload that has failed in production on Sunday, we still have that data. And it also allows you to query those logs. There are actually various ways of setting this up. Your favorite cloud provider should have a tool for this. If you use Coiled, for example, we do this for you. And like here we just see a simple example where we query some logs that we've collected for a cluster. And we're looking for some information on memory usage because we saw something that was kind of fishy about that on this particular worker. If you have structured logs, even better, then your queries will be much more powerful than this thing. Now, we've talked a bit about logs. And in that case, I think with Dask in particular, we should also talk a bit about events. That raises the question, what are events even? And the answer to that depends on who you ask. So if you asked OpenTelemetry, one answer is like, semantically, events are just named occurrences at an incident time, which is, well, thanks. I guess that's like more of a philosophical answer to the question. The more practical answer from OpenTelemetry is that it's essentially structured logs. They tell you one specific format in which they want to have these, and then your logs are just events. With Dask, it's a little bit different. In Dask, events are mostly structured logs as well. But we also in Dask have a separate data stream for those. So it's separated from your average log stream. And also events happen in a lower frequency because of how we handle that data stream and because there may be more consumers, so more processing happening on this side, and we don't want to overflow this. So how can you actually access any events in Dask? Well, you can on the client, you can subscribe to a topic. So this is a topic-based system. We have like separated various data streams of events into larger areas of interest. And you can, let's say, like, tell me everything about, say, P2P, tell me everything about a specific worker. And then there are various very specific events in there. You can also register a scheduler plugin if you want to handle this more from the cluster side than from the client. And then in there's a log event hook. Now, so much for logging and events. Let's actually check what this tells us about what happened in our cluster. Now, here once again, we have all the logs from our coil cluster. I might actually have to refresh that. And we see there's a lot of useful information in there, but also there's a lot of information. So I don't really know where to start with that. So logs, helpful, but only if I know what I'm looking for. Let's very briefly look into events, if they're any helpful for us. Well, at the very least, we have something that very specifically tells us that P2P failed. So what we can do with that is we can intercept that event, and we can, for example, create an alert, or we can flag that operation and say, like, hey, you need to look into this. This failed, and it failed because P2P went wrong, so check that part out. We kind of inferred that from the logs already, but this is the structured information that makes it a lot more accessible for us. And just to show you all, there are a lot more events within Dask that we can hook into. It really depends on what you're looking for. But still, like, I don't know where to start with my analysis. And for that, I would actually like to have something that I can just take a brief look at and then roughly know what's going on in the cluster, what happened, and try to drill down from there. And that's where metric comes in. So metrics are all the measurements we take at runtime about our system, and then we collect that, we store that, and we can then start to paint a picture of what happened in that system over time. And usually, we then use some visualization library like Grafana or something else that allows us to create charts about this, make this visually perceptible, and we can drill down into that information and figure out more. In Dask, we actually expose quite a number of metrics. That's from very basic stuff like how many workers does the schedule actually know about, to much more detailed information about, say, memory breakdown of different workers, like how much memory on this worker is actually managed by Dask, how much data did we spill, is there maybe even some imbalance between different workers, and we might have to worry about that. I won't go into detail about this in this talk. If you're interested about all the Prometheus metrics that we expose, please head over to the documentation or head over to the call booth later. We can discuss some stuff there. Now, similar to centralized logging, you also want to centralize your metrics. We have the same problems. If the worker dies, we can't access any metrics that the worker might have stored somewhere in memory. For that, Dask has a native Prometheus plugin. And what that does is that it allows Prometheus, which is a metric time series database or any compatible system really, to continuously poll the cluster for metrics. And then it can use that, store that information, and once again allow you to query it after the fact. When we have those centralized metrics, what this enables are those rather powerful dashboards that I also hinted at already. So let's maybe take a look if there's something in there that tells us what happened. The important bit is we need all the time. Now we see there's quite a bit going on. In particular, like this area is the stuff I'm interested in. Lots of information. many things are going on. And now there's one piece of information that I'm quite interested in. If I take a look at just everything. Oh, what's this? What I see here is now, okay, it looks like I've cut this off. It's actually use Coil for that because I don't want to reset all this stuff. Now here we have a plot, and this is bad. What we see here is like, it looks like our worker has run out of memory, and not out of memory, sorry, out of disk space. And we all know if we have something that writes to disk, which P2P actually does, that's bad because if we can't write to disk anymore, things fail, things blow up. So it looks like that is what happened here. Let's maybe take a moment to confirm that suspicion. And probably there's something like a no space left on device exception or so that Python usually throws. And let's see. Yes, that's what happened. So together with metrics and the logging information, we're now able to like dive deeper into what has happened on my cluster and figure out what exactly the problem was. I'll be honest, that's a bit of magic. You have to kind of know what you're looking into, but at least you have all the information available to you and you can try to make sense of things. Now, with metrics, we not only can just create beautiful dashboards, but we can also use that to create alerts or to create flags that tag clusters and tell us either proactively that something might be going wrong. So in that case, it might be nice to have an alert that tells us as soon as some worker goes above, say, 95% of disk usage, that we should look into this because this might hit a threshold where things will just not work anymore. At Coil, we often actually use this stuff to tag clusters after the fact to alert people to a situation that they might want to look into. So on this cluster, we already see here now, like, we're tagging this for a lot of disk usage. So yeah, we actually have a flag already that tells us, hey, something is fishy about that, please look into it. We can do a lot more stuff. We see that there's network traffic going on. That's in a distributed system. I mean, network traffic kind of makes sense because you have to send data around. But then again, you also still want to minimize that. So depending on how much network traffic is actually going on, you still may want to look into this. And similarly, you can use more metrics to just also understand other situations like, is your scheduler continuously running at 100% CPU usage? That's something you also need to look into. But yeah, so much for our small example. I'd like now to talk a bit about two other use cases that we've actually seen in the real world where we've had used metrics to help us figure out certain situations and make decisions based on those. Like the first example is we wanted to know for Coil what the good default instances would be for our customers. And what we looked into there was we compared AWS burstable instances, which are a bit cheaper on the base price, but you still have to pay like a little more money if you use a lot of CPU. And basically, if you just burst, that costs more. And then you have M6I instances, which are just normal machines, quote unquote. And what we see in these graphs here is, first of all, the M6I instances on this workload that's more or less network and disk bound because it's large array computation. M6Is are a lot faster. Like they finish a lot earlier. And also, if you trust me on the numbers that you can't read right now, bandwidth or throughput is much higher. Similarly, if we look at a different workload that's actually not really network or disk bound, but much rather CPU bound, we see that, once again, M6I instances are a lot faster to finish the job. And also, we see this weird red stuff in the top graph from the burstable instances, and that's stealing. And that stealing basically, in this case, just took away some of the available CPU time that we would have had that we would have needed to get to full 100% utilization of that machine. Now, after looking a bit into the documentation of these instances, what we actually figured out was that, well, yes, first of all, this result totally makes sense because the instances that we picked were the same basically on the CPU type and the amount of memory that they had, but the burstable instances actually have worse network and disk hardware. And similarly, we figured out that the stealing was actually something from the hypervisor that went in there. And more importantly, what we saw is that if we actually have these CPU workloads, the burstable instances were actually more expensive than the non-burstable ones. So like these are slower and more expensive per minute. So they're a bad choice for these cases as well. So in the end, we figured out for the data science and data engineering workloads that our customers have, like we should pick non-burstable instances because they're a much better fit essentially. You can read more about that if you're interested in our blog post. I won't go into too much detail here. Next use case that we have is actually data-driven design that we do within the open source Dask team. And for that, we have a bunch of different benchmarks that we run to make sure that any sort of changes we do where we expect a performance trade-off to occur, that we understand what's going on and that we don't catch like regressions and make something that used to work very nicely a horrible experience for the users. So in this case, we were actually trying to improve the shuffle implementation in Dask recently. And if we look at this first plot, blue means it's much better. So we see like for analytical queries, this was a great implementation. Like we should use this now. The problem is those are all analytical queries, and they have in common that they reduce the data set greatly. And that's something that actually we apparently over-optimized for. Because now we have this graph, and red means very, very bad, in particular if it's this huge red bar that we see. And for some other workloads that were more data processing workloads, so you don't reduce the amount of data, but you much rather do some transformations and write it somewhere else, it turned out that this change that we made introduced a performance regression of a factor of 3x or even more. So yeah, as a result of that, we decided, well, we can't just pick this change. While it's nice for analytical queries, there are also many people who worry about data frame or data transformations, and for those, it would have been a horrible experience. So we need to make the change or redo the change, iterate over it, and we can't just accept it right now. So much for metrics and logging, and in general, telemetry. Now I want to talk just a bit about the diagnostic tooling that we have available in Dask. As I've said, like it's nice to have telemetry, but if we can't interact with that, it doesn't really help us. And while we've seen how centralized logging and centralized metrics can also already help us with that a bit, there's some tools that we have built into Dask that are rather specific for the Dask user. Now, I've already shown the dashboards and all the cool things that they show. We can see the task stream, what's actually going on. We can see like GPU utilization. We can see GPU memory. All that is very helpful because once you've understood what's going on there, you can see what's happening. You can see certain patterns. You can see certain situations. The downside of that is, while that is very useful if you look in the right moment, these plots are all ephemeral, which means we don't store any of that data. It's just a real-time representation of what's happening. So if you don't look in the right moment, and I suspect nobody looks at their production workload at 3 a.m. on a Saturday morning, you miss what's happening. So one question that we ask ourselves is like, hey, can we actually like maybe store a subset of that data to understand better what's happening in terms of performance? And that's what we have performance reports for. What this does is it's a context manager that you can wrap around your workload, and it then collects a subset of the data that we can show on the dashboards, stores that, and compiles that into one big HTML file that you can share. First of all, you can share that among colleagues, but you can also share that among Dask people who might know more about Dask and use that to analyze certain situations. Let's take a look at a quick example here. Now here what we see is, first of all, we have some summary statistics. We have the task stream. So we see what happened where. Then we also have some system information. And also, interestingly, we have some profiling information from the workers or from the schedulers that help us understand, hey, what are they actually doing at the time? Now, to get out of there again. So, profiling. Let's talk about that a bit. This is something you won't get around if you really want to understand the performance of your workloads. You might see some patterns already in the metrics, like, well, I'm flatlining on disk throughput, or I'm just exceeding hardware that I have. Like, I can't use more than all the CPUs that I have on my machine. But sometimes there's also things where there's just structurally something in your code that slows you down. And that's what profiling helps you for. Within Dask, for that we have built-in a statistical profiler that you can reach at the profile endpoint. And that's quite nice because this profiler, it's not perfect because it's a statistical profiler, but it's always on. So as soon as you see that something looks weird about the performance of your application, you can just head to that endpoint and directly dive into the profiling information that's available. We also aggregate the data over the entire cluster. So you can get like an aggregate view of the entire workload, or you can drill down deeper into, say, specific periods of time, if you're just interested in, say, the last 5 minutes. Or you can drill down into individual workers. Downside is, this is Python only. So if you're using C code, Fortran code, you don't see any of that. And once again, it just has flame graphs, no rich timeline. So if you want to have some more detailed information, I recommend you to look into the Dask PySpy package. Now, the last thing that I want to hint at is data frame analyze. That's something that we've just recently released. Like, if you know Dask, you might have heard that we've recently released a whole new rewrite of a data frame API that allows us to have a much better high-level representation of workloads. And this is a first step toward making that also useful for understanding performance characteristics. If you know databases, you may know analyze call in there. What we do here is we basically run the workload and calculate all sorts of statistics about the workload that happened. Like, this is a preview version. This is still very raw. But what we can see here already is like, how many partitions do we have? How large are they? Is there imbalance? Like, on the right, on this fuse IO, if you see that, we have on the very left side, that's the minimum size, that's 50 megabytes. On the right, it's 350 megabytes. So there is some imbalance. And we can use all that information, understand that if we have plots like these available. Now, if you want to learn more about our changes in the data frame API, head over to Patrick's talk right after this one in the other room. He'll talk a lot about this. So zooming out, what have we learned? An observable system lets us ask why something is happening, not only what's happening. Logging and metrics are super important for that. And good diagnostic tooling is also something we can't miss here. Dask has a lot of stuff built in here. But if we really want to utilize that, we need to have centralized and durable collection of that data. And that's something where a company like Colt can help you with that, so you don't have to set it up yourself. Thank you.